of Computer Science, Engineering and Information System, VIT Vellore. We both have very long association since I think 2013 or 14, right? Professor J.V.R. Murthy introduced Professor Ashwin Kumar to me.
I think 9, sir, 2009.
2009.
Yes,
Thank you, Ashwin Kumar Garu, for correcting. Right. I have seen the academic strength of Professor Ashwin Kumar. Right. He produced a lot of PhDs. And I am glad to have association with Professor Ashwin Kumar. Now, without wasting much time, I request Kiran Mai to introduce Professor Ashwin Kumar Garu to the audience. Thank you.
Professor Ashwini Kumar Cherkuri is a director of the Center of Artificial Intelligence Research and a professor HAG in the School of Computer Science and Computer Science Engineering and Information Systems at Vellore Institute of Technology, Vellore. He has over 24 years of academic and research experience with research interests spanning machine learning, information security, quantum computing, and post-quantum cryptography. His work particularly focuses on encrypted network traffic analysis and advanced machine learning techniques. Professor Ashwini Kumar has an extensive publication record with more than 200 research papers and over 5,500 citations, along with an H-index of 36. He has successfully led multiple research projects as principal investigator, securing funding worth approximately $10 million from various Indian agencies. He has guided 8 PhD scholars and mentored several international interns. Since 2020, he has been consistently recognized among the top 2% of scientists in India in AI and machine learning, based on a study conducted by Stanford University researchers. He is also an author of a book on encrypted network traffic analysis published by Springer. Internationally, he served as an adjunct professor at UCSI University, Malaysia, and is currently a visiting professor at VCD, Lithuania. His contributions have been acknowledged through several awards, including Young Scientist Fellowship from the Tamil Nadu State Council for Science and Technology, Inspiring Teacher Award from the Indian Express, Educator Excellence Award from VMware. Professor Ashwini Kumar serves on the editorial boards of several international journals and is a senior member of IEEE and ACM. He is also the vice chair of IEEE Educational Task Force on Data Mining and distinguished speaker of ACM, delivering invited lectures at various institutions worldwide. From 2015 to 2018, he served as a dean of the School of Information Technology and Engineering at VIT. He has organized numerous international conferences both in India and abroad. In addition, he actively contributes to the curriculum development, academic planning, and institutional initiatives, playing a key role in enhancing teaching and learning process across institutions. May I now request Professor Ashwini Kumar to kindly share his expertise and experience in quantum computing fundamentals to algorithms. So please.
Thank you, madam. So I'll share the screen. Yeah, is the screen visible?
Yes, sir.
Okay. So my voice is also audible, right?
Yes, sir. Audible, sir.
Okay. Thank you. So first of all, I would like to thank Professor Krishna Prasad Garu for inviting me to deliver the lecture today on the topic of quantum computing, fundamentals to algorithms. As Professor Krishna Prasad Garu was mentioning, we had a long association thanks to Dr. J.V.R. Murthy Garu, who actually introduced Prasad sir to me when I was looking for the doctoral committee members for my students. So from then onwards, we were continuously interacting for both academic research and other related activities. So once again, thanks Professor Krishna Prasad Garu for inviting me, and also thank all those participants. I see a very good response for this initiative from the JNTU Kakinada. More than 120 participants I'm seeing. I understand that the participants are mixed in the sense both there are faculty members as well as the research scholars, maybe the postgraduate or even undergraduate students. So my lecture for the next few 1 hour or 1.5 hours would be focusing on the quantum computing and quantum computing per se. Also, I will provide the basic fundamentals of quantum computing. And probably I understand that this is a lecture series. There are a couple of other sessions that were held on the quantum computing fundamental aspects, but I will give a different perspective of the quantum computing, try to provide a different lens towards the way we understand quantum computing in a way that we need to see what is its true potential, where actually it would support us, and what is the underlying phenomena that actually supporting the various applications that people are talking about, and where is the current state of art, and what are the fundamental algorithms that this computing will support. So this would be my scope of talk. Before we enter into the actual topic, let us understand one fundamental aspect. Imagine we are having a coin which does not balance on any of its edges, right? It's a true coin. And we know that it has two states called head as well as tail, right? One could be facing up and another one is in the facing down. So it has two states, heads and tails. If we have two coins, obviously the number of possible states would increase, in the sense we will have either two heads or two tails or head tail, tail head, right? Because we have two coins. Number of states for the two coins would be increased to 4 states, meaning what actually is happening when with the two coins we are getting 4 possible states for we have 2 coins. Imagine if we scale it up, we have 3 coins, means now we are having totally 8 possible states, starting from 3 heads to 3 tails. So if you see here, we are actually, when we are increasing, meaning, when we are having 3 coins, we are getting 2 power 3, 8 possible states for a set of 3 coins. If we proceed further, meaning if we imagine we have n number of coins, obviously we will have about 2 power n possible states coming from these coins. Right? We all know this, being a computer science domain persons, we all know that this is the possibility scenario. But what is the connection this with the quantum computing, what we are going to talk? That I will connect it maybe after a couple of seconds. Now, we have seen so far coins and their possible states. Now I am taking a different geometric structure. So imagine that I have a standard 6-sided dice, right? So when you look at a single dice which has 6 sides, obviously we are going to have 6 possible states with the numbers ranging from 1 to 6. We have all seen while playing various in-house games in our day-to-day life. Imagine we have 2 dice. We have 2 dice, then obviously the number of possible states for the 2 dice scenario would range from 11111 to 66 in the diagram that is shown here, right? So meaning what? We have dice 1 here and the dice 2 here. You can see all possible states for a 2 dice system. So meaning what? When you put it in a mathematical perspective, with 2 dice, we are getting 36 possible states. Meaning what? With 6 sides for each dice, and we have 2 such dice. So 6 square, which are nothing but 36 possible states for a 2 dice system. Now, when we follow this same pattern, when we extrapolate to 3 such dice, obviously we will have 6 power 3, meaning 216 possible states. So again, as usual, when we scale it up, imagine we have n number of dice, we are going to have about 6 power n possible states. We have seen the scenario of a coin, wherein which with n coins, we are getting 2 power n possible states. We have seen now a scenario of dice. If we have n number of dice, we are getting 6 power n possible states. Okay. So 2 scenarios we have seen. Now, the question is how this is related to quantum computing, or why we are discussing this particular concept when the talk is on quantum computing. So let us think on that, but I will proceed. I have one question to ask. Now, when I have these coins and dice as the geometrical structures in my hand, I wanted to know how much information these particular geometric structures, say whether it is a coin or a dice, can carry. This is the question I have. So how much information coins can carry, and similarly the dice can carry. So to understand that particular question, imagine I am considering the colors of the rainbow, right? We all know that there are about 7 colors in a rainbow. So my problem is to encode, or rather to represent, these 7 colors of the rainbow with different possible configurations of coins or different possible combinations of dice. That is the problem scenario I have. I repeat, what is the problem scenario? I have 7 colors of a rainbow. I need to encode these colors information either through coins or different combinations of dice. How do I do it? If that is the scenario or use case I have, how many coins I would require, how many dice I require? Since I have 7 colors, the solution space I would require in the case of coins is 3 coins. In the case of dice, it is 2 dice. So meaning if I am representing the 7 colors through coins, I require 3 coins. If I am using dice to represent or encode the 7 colors of the rainbow, I require 2 dice, right? Why? You can see this. I can encode red color if it is through coin as head, head, head. In the case of dice, I can represent as 1, 1. So you can see 1 to 7 different colors, and the way of encoding in the form of coins and the way in the encoding of the information in the form of dice, right? So I have totally 7 states, and if I'm using coins, I require 3 coins, meaning 2 power 3, which is getting 8 possible states. Of course, I have only 7 states to represent, but with I am using coins, I have 8 possible states. So I can easily encode the colors information. In the case of dice, if I take 2 dice, if I take only 1 dice, so I have only 6 states, but actually I have 7 different colors. So obviously I require 2 dice, and then I can encode the colors information with the 2 dice. So what is this example, or what is this particular information represent? Of course, the same thing what I have narrated here is given in the form of illustration. Now I will just skip this. So a coin carries less information than a die, and hence it takes 3 coins to represent or to encode 7 colors of the rainbow, whereas if it is dice, I require only 2. So coins carry less information, dice carry more information when compared with the coins. But why it is so? Because of the simple fact that coins are able to represent only 2 states, whereas dice are able to represent 6 states. So meaning what is the inference finally I can derive is that something with the 2 states can carry the smallest amount of information that is possible, right? So this is the inference that I can derive from the example of representing the information of a rainbow in the form of coins or dice, or for that matter, any use case if we take. So now, again, what is this statement can infer or can come out of what we can relate it to the quantum computing? Now, fundamentally, we all know that the computers uses the bits as the fundamental unit of storing and representing the information. These bits would carry, two states, 0 or 1, right? So just we have on, off, true, false, 0 or 1. So we have only 2 states. So meaning the fundamental classical bits what we have are able to represent smallest amount of information. But imagine if I have some structure or if I have some mechanism that can carry not just 2 states, but rather multiple states. Like the example in the case of dice, which is showing about 6 states, right? With a single dice, I could represent 6 states, 6 different states. If I have another, a memory unit or a fundamental computing unit that can carry multiple states, not just 0 or 1 in the case of a classical bit, right? So a classical bit, we are able to have only either 0 or 1. With 2 states, it is able to carry or represent or encode the smallest amount of information possible. But imagine if I have something else that can encode multiple states, I can carry more amount of information, right? So number one, what we said about is representing more amount of information, and not only representing, but also about computing, but also about communicating, right? So if we are having a mechanism that can either represent, that can represent, compute and communicate, then obviously we can have much amount of information that can be represented, computed, and as well as communicated. So that's where our quantum computing, which is coming into picture. I think some of you or all of you might have heard a fundamental unit of quantum computing called qubit, wherein which people are able to represent not just 0 or 1, but rather multiple states of information, right? Multiple states which can qubit can represent. So that's where the connection what I wanted to connect with the example scenario of the classical coins and as well as dice. Now we all know that the digital computers have progressed in the past 60 years or so. From World War II onwards, they have come from a long way, right? Of course, the term computer was there in early 1600s onwards, but when we say computer, we are all referring to the digital computers, right? We all know that they have progressed a lot, especially after World War II. We have come from mechanical computers to the electronic computers, right? And also we have the internet and etc. Now we are living in a digital world. So if you look at all that, the bits are the fundamental units of information. When we say bit, obviously, which is representing either 0 or 1. So we can encode whatever is the information that we wanted to represent using the bits, which can encode 0 or 1 in the form of words, characters, even pictures, whatever the information we have. Fundamentally, we are using the classical bits to represent the information. Once you have that encoded information, what we are doing is we are using the logical gates. We all know that we have different logical gates called OR gate, AND gate, NOR gate, NOT gate, etc. Using these multiple logic gates, we are able to build circuits and then finally able to process the information. So meaning what? Our fundamental unit of information processing is the classical bit, holding either 0 or 1 as the state. Now, with that particular context, let us take one particular problem. Imagine we go to one of the largest library, right? So obviously it has multiple books, several millions of books we have. Now our job is, say, take an example, my task is to find one particular sentence in a book among billions of books that are there in the library. Now, how do I do it, right? So how do I actually go to this library? When I say go to library, inside the library, how do we search for a particular sentence in a particular book across billions of books? And remember, the task what we have is complicated because we do not know where the book it is. in the entire set of billions of books, right? So how do we do it? Obviously, what we can do is, we go to the librarian and ask his help. Of course, he's a human, right? Even if it is a fastest human, who can actually read a book in 1 second, what would be the time actually that would take to scan through the billions of books that are there and then find a particular sentence that you are looking for would take, it is approximately about 31 years by a human individual who can read a book per second. I'm not sure we have any human that can read per one book per second until and unless, we have seen in a film of Robo where Rajnikant can read and at the swipe of a second reading an entire book. I don't know whether we have any human. But in case even if it is there, it takes about 31 years to scan through all these billions of books and then find this sentence, right? But no, imagine instead of a librarian, imagine that we have a different setup where we have somebody who can somehow be in every aisle of the library at once, flip through all books simultaneously, right? Flip through all books simultaneously. That is the one of the underlying sentence. So, and hand you the answer in minutes. Now, that means there is somebody who can go to every aisle part of the library and flip through all books simultaneously. Then, we can get the answer in a fraction of minutes, right? So this is where the fundamental difference between a classical computer and a quantum computer would come, right? So, but the question is, imagine how do we understand why that second librarian who is able to go to every aisle part of the library and then scan through all books simultaneously is able to perform, in the task of finding a particular sentence in a fraction of minutes. We need to understand how actually, building such particular librarian, or meaning, building such a system that can go to these aisles of the library at a time and flip through all books simultaneously. How do we build such a system, is or how hard it is to find such person or to build such system. That is one use case or a scenario. Not only that, now imagine there is another scenario where, there is a telecommunication company wanted to manage, different SIM cards that they have, and they wanted to identify what are the SIM cards that are valid and what are not valid, or, kind of organizing their SIM cards. So when there is a customer request arrives, the company wants to verify whether a particular SIM card is there in that pool or not. Now again, if you look at this particular problem, which is similar to the problem that what I spoke a few seconds back, these are all the problems which are actually kind of search problems, which are, again, when I say search over an unordered or unsorted database of the information system. Searching over such particular databases is computationally very, very, very hard, right? So in a classical scenario, when we have an algorithm, the algorithm would require, in a worst case scenario, of order of n, where your n is the number of elements in the system, right? So take an example. We talked about library where you have about billions of books. So meaning, in a worst case scenario of referring to or scanning through all billions of books. I said billions of books, but again, in each book, there may be hundreds of pages, right? So these are all the problems which we are referring to. Even this is one of the finding a valid SIM card or a valid SIM number is one of such particular problem, right? So what if suppose, we have a computer that can take all such billions of books or such millions of numbers, put them in a particular state, what that quantum computer calls that state as the superposition state, where in which all those states are parallelly being available for the for a particular function. That function, we call it as a Oracle function, which can look at all those possible states parallelly and then provide the answer, right? Whether we are verifying for a particular sentence or whether we are verifying for a particular valid SIM card number, so parallelly that can scan through this particular unordered or an unstructured database and provide the answer or a solution. And such type of algorithm, what is the exact algorithm that we have in a case of quantum is called Grover algorithm, that is able to reduce the search problem from order of n to order of root n, right? So this is one of the solution coming from quantum computing world called a Grover algorithm that we will discuss in the upcoming slides. This I think I will skip because all of us know that, we all know that the evolution of computers starting from vacuum tube to the current day silicon chips, how this, the digital computers have evolved, right? So I'll just skip this and then I will go to the quantum. So one of the another interesting problem of the classical world is called traveling salesman problem, wherein which we have imagined a person who has to visit about 10 cities. All of us know which is a classical problem when we are talking about data structures or algorithm analysis. He need to visit 10 cities and return to the home. And of course, he has some optimization task so that, the task is to touch all these cities in the shortest possible route so that, he can save the fuel, right? And we all know that this particular task will scale up with the number of cities that he should, he has to visit. So take an example, even with that 10 cities, the number of possible routes to scan through to understand what is the best possible route, that itself is about 10 factorial, meaning around 36,28,800 different routes to be scanned through to identify what is the best possible route. So meaning, you can think of with the number of cities grows, meaning the number n goes, the number of possible solutions that grows exponentially. You can very well see that with the 20 cities, the number of possible routes need to be explored is 2 quadrillion routes. The more the number of seats, the problem gets untractable, right? So we are moving from the classical towards the quantum. I'll just directly go to the quantum aspects where the quantum computers are actually the kind of problems what we spoke just now about the search problems, where actually they are going to make a mark, especially in a scenario or a problem environment called drug discovery, where actually the companies have to look at multiple millions of molecules to scan through and identify a better drug that requires a huge search space to be scanned through, and that's where the quantum computers comes into picture. Meaning, when there is a drug discovery task that needs to scan through millions of compounds, that actually requires a solution coming from quantum. Similarly, the other area where the quantum computing is going to make an impact is the security. Essentially, we all know the cryptography is a domain which is providing security algorithms towards building security protocols and solutions. We all know that cryptography has two branches fundamentally called symmetric and asymmetric cryptography. Both actually, if you look at these symmetric and asymmetric algorithms, are fundamentally are getting impacted because of the quantum computing. And also quantum computing, one side it is impacting the security and also it is providing security as well. Both are there. If you look at the symmetric cryptography, there actually the challenge is that the quantum computers are able to identify the symmetric key, which is the classical key which is used as a commonly between sender and receiver. Quantum computers can use the search algorithm such as Grover algorithm so that the symmetric key can be identified. Okay, one of the solution for this particular problem is to enhance the key space of key size of the symmetric key. The another one is the asymmetric key, wherein which you have two types of keys called public and private keys for any node. the quantum computers using the algorithm called Shor algorithm, people are able to break asymmetric key cryptography, protocols or algorithms. These are the two challenges that quantum computing is bringing towards or impacting the security. At the same time, the quantum computing is also able to build security solutions through quantum key distribution. So the fundamental challenge of sharing the symmetric key can be solved with the help of quantum key distribution rather than going for asymmetric key. In all classical scenarios or in all our current security solutions, what happen is we use asymmetric key to share the symmetric key between the computing nodes or communicating nodes. So as I said a few minutes back, the Shor algorithm is breaking the asymmetric key. Quantum key distribution can help to exchange the symmetric key between the nodes. So this is, when I say these two things, this is the impact of the quantum, adverse impact of quantum on the security. This is the benefit that quantum computing is providing towards the security. So one, the impacts of our solutions or the applications of quantum. One, I talked about, the drug discovery. Another, we talked about the security. And the third dimension is about optimization. Wherever we see a lot of optimization problems, one of the beautiful use case we talked about finding the shortest path. Similar such type of optimization problems we can see in day-to-day life and as well as in the logistics. There also the quantum computing is going to play a major role. Now, having discussed all this, let us see what is quantum computing. So quantum computing and what is the difference with the conventional computing. So conventional computers uses the voltages flowing through the circuits and of course bits and then circuits and gates, and then they will be controlled and manipulated using the fundamental mechanism called classical mechanics. Whereas the quantum computer, they follow altogether different mechanics or laws of quantum mechanics. Now, this is where the beauty of the quantum mechanics bringing different features such as superposition, entanglement, decoherence are the quantum mechanics principles that are bringing to quantum computers a different set of the dimensions so that the quantum computers are becoming powerful. Now, let us understand what are those features that are quantum mechanics are bringing to the quantum world. Number one is that we are moving from, in the computing per se, we are moving from computing over the real numbers to the complex numbers. That is the reason why those who are doing research, or especially the postgraduate or research scholars, you will see that in the literature or when we are reading about the quantum computing or when we are computing with the quantum computers, we see that the numbers that we see are nothing but the complex numbers. Of course, any number we operate on a day-to-day basis also complex number. Even a real number is also complex number, wherein which your complex element is 0. But in a quantum, we are actually dealing with the complex numbers. Okay, fundamentally with the complex numbers. That is one of the unique feature. What is the advantage of that? I think again that's an altogether different topic that need to be discussed in detail. So that is one of the features. So moving from real numbers to the complex numbers is one of the feature of the quantum computing. Another second feature is that moving from single states to the superposition of states. This is another unique feature that is coming on the quantum computing, wherein which you can notice that every object exists in a unique place and in a well-defined state, whether we are looking at it or not looking at it. That is what is the fundamental philosophy, right? Even in a day-to-day, conventional computer says, meaning what? When you are looking at an object that's in a well-defined state, that even when we are measuring it or not measuring it, when we are looking at it, when I say looking at it, meaning, whether we are accessing it, not accessing it, it is in a well-defined state. Of course, this is the true for large objects, but in the quantum computing, it is false when it comes to the objects that are very small. What do we mean by that? Meaning that when there is a particle, that particle is very, very small to the extent that, at very, very subatomic particle level, meaning what? At an electron level, such level, objects will behave in a very, very different manner. There is nothing like a well-defined state for such type of objects when they are at a small level. And at that level, those objects will lie not in a well-defined state, but rather they would be in a superposition state. What do we mean by superposition state? It means that those objects will be simultaneously in multiple states at the same time. Meaning what? Few minutes back, we talked about a classical bit saying that it is either in the 0 or 1, meaning it's a well-defined state. But a superposition state says that object would be simultaneously in multiple states at the same time, right? So that is what is the superposition state. So we will see what do we mean by superposition in subsequent slides. In opposite to the superposition, we have a state called measurement state. When they are in superposition, objects will be in multiple states at the same time, but when we measure them, the superposition state will collapse and will reach to a well-defined single state, right? So superposition state is a state with multiple object to be there in multiple states at the same time, but when we measure it, that would get settled down to a single defined state. And remember, all these things are nothing but the gate operations that we perform in the quantum computing. Suppose I want an object to be in multiple states, meaning the superposition state, I need to apply a gate. Similarly, when there is an object in the superposition state, I wanted to define it to a well-defined state. Again, I need to apply a gate. For each of these tasks, I have multiple gates. Say, take an example, I have a gate called Hadamard gate to get an object into a superposition state. When I say gate, obviously, if you look at fundamentally, it is mathematically defined in the form of a matrix, right? So for Hadamard gate, there is a matrix representation. Similarly, when we say measurement, again, measurement gate we will apply, and then it will finally fall down to a single well-defined state. But the beauty of this measurement here is that when it is settling down into the defined state, to which state it will fall down, nobody knows. That's where the probability comes. Meaning what? When I say a qubit or a system is in a multiple state at a time, meaning what? There are states like x1, x2, x3, and so on, multiple states. And now an object is in multiple states. Now we are saying we apply a measurement, it will fall down to one of the well-defined state. Now the question is, to which state it will fall down? That is the probability, right? Depends on the probability amplitude of these states. That's the beauty of quantum computing, right? So this is one of the features of superposition. The next feature is computing by moving away from locality to the non-locality, right? So to just give a single or a simple analogy is that we all know that while talking about operating system, especially in the memory management, we all know that the memory objects that are referred, when we refer to a particular element in a location I, most likely that processor may refer to the element which is in I+1 state or an I-1 location, right? So instead of computing in such a locality too, the quantum environment will take us to non-locality through a phenomenon called entanglement, right? Even if two objects, if they are entangled, even if they are not there locally, meaning they are there at a different location, two entangled objects can impact each other. That's what is the phenomenon of moving from locality to the non-locality. Then another feature of the quantum world is that we are moving away from deterministic laws to the probabilistic laws. Okay, so where this is coming, few seconds back I spoke about to which state a superposition state will collapse to when it is measured is what is determined through the probabilistic laws. So the laws of quantum mechanics states that we can only know the probability of the outcome, but not exactly to which state it can be falling down when it is collapsed, nobody knows. We can only tell the probability of outcome, not the in a deterministic manner, right? And another interesting feature of the quantum world is that we are moving away from certainty to the uncertainty, right? There, for this particular purpose, there is a important principle called Heisenberg uncertainty principle, which says that the more accurately we know about the position of a particle, the less accurately we can tell about its momentum. That's the Heisenberg uncertainty principle. And also, we also call it as, the consequence of this is called wave-particle duality. Meaning what? To give a simple analogy, imagine that there is a moving train, when there is a moving bus or a moving car, which has, or any object for that matter, which has the momentum. When an object is in momentum, meaning, when a car is being with a velocity of say about 100 kilometers per hour, it is moving, we cannot precisely say what is the exact position of a vehicle at a particular time, because it is in a momentum. The moment you nullify the momentum, we can tell that, hey, yes, this particular car is in this particular location, right? We all know that. So this is called Heisenberg uncertainty principle, saying that we know more about one particular parameter. Obviously, that makes us to know less about another parameter. So this is another one of the fundamental principle that is deriving the quantum computing. Based on all these principles, we have these, whatever the quantum computers that are working now, moving from real numbers to the complex numbers, moving from the single states to the superposition of multiple states, moving from computing over locality to the non-locality through entanglement, moving away from determinism laws to the probabilistic laws, and then fundamentally moving from certainty to the uncertainty. If you notice, on whatever that we have on the left side of it is the classical, whatever that we have on the right side of it is the quantum, right? So these features are making quantum computers, unique, not similar to classical, and also bringing computing power to the quantum, right? So these are all some simple illustrations that I just wanted to show for a better understanding. We all know that a classical bit, we say it is either on state or it is in the off state, right? So this is the classical bit. This is the classical bit, right? So whereas if you look at the quantum, the bit, we call it as the qubit, it would be there in multiple states. You can see that it either spins left or it can spin right, so that it will have multiple states between 0 and 1. We know that there are about infinite number of numbers between 0 and 1. So the qubit can be in any possible states between the 0 and 1, right? Next, when with such phenomena, when we have, imagine not one bit, now imagine we have 2 bits. We know that for 2 bits we have possible states such as 0, 0, 0, 1, 1, 0, and 1, 1. When it comes to the same extrapolation of the quantum, we can see that the quantum speed up can come. Because all these 4 possible states being available at a time. Now we all know that when we are running, say take an example, a classical gate of AND gate, we say 0, 0, we get 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, right? But when it comes to, that goes in a sequential manner. But when it comes to quantum, we can notice very well here that the all possible 4 states are being available at a time, and hence gate operation, all these 4 possible states can be executed in parallel, so that the outcomes of 0, 0 to 1, 1 can be available to the program or the for computing environment at a time, right? That is what is called quantum speed up. What is shown here on the slide is with two bits, you can extrapolate to multiple. So this is a simple table that is giving fundamental difference between classical and quantum, right? What is the interesting aspect that one should notice here is that, we all know that we measure quantum, we measure the complexity of the classical algorithms in terms of polynomials, right? Whereas in the case of quantum, we call the complexity class as BQP, meaning bounded error quantum polynomial time, right? So the reason is that, quantum inherently has a lot of errors that are created because of the environment that is in which the quantum computing computers operate. People try to isolate and then make noisy, free quantum computers, but what so far we have is called NISQ, called noisy intermediate state quantum computers, and inherently they have noise. And hence, what we call the complexity class of algorithms is called BQP class of algorithms. This is one of the striking difference of classical with quantum, right? So of course, same thing, but what I spoke about. So the another slide of difference between classical and this one. I will directly go to one of the, I'll talk about the algorithm a little later. Yeah. So this is the traditional bits, and as well as the few seconds back we discussed this. We have seen the traditional bits of having 0 and 1, whereas the case of quantum we have the representation. What you can see on the right side of the screen here is talking about the quantum bit. So this is another representation purpose. You can see that arrow is moving across multiple locations of the sphere, right? This particular sphere, we call it as, I'll just bring the pen. So this particular sphere structure, we call it as block sphere, right? So you can see very well that, I try to see, yeah, you can very well see that, the state of the qubit is getting rotated across multiple points on the sphere. Now, this rotations happens with the help of, the operations that we perform with the help of different gates. Now we have multiple gates to apply. Now you can notice, ideally, if we all know that if you take this particular spherical structure, if you ask how many points would be there, infinitely there would be infinite number of points. Meaning what? If you see here, a classical bit is shifting between 0 or 1, whereas a quantum bit is shifting across multiple, the states between even 0 to 1, right? So that's the beauty of the quantum computers. What we have seen is for single, but imagine if it goes for, more than 1, obviously from 2 qubits, we will have 4 states, and imagine with 3, we will have 8 states. All these 8 states would be available in parallel to the computing environment. So meaning whatever the, whether you use an IBM quantum environment called Qiskit or whatever it is, when we say 3 qubit system, we are able to get all possible states available to the, the computing environment. So because of that, what happens? Adding qubits increases the storage exponentially. So now you can very well connect with the example what I spoke a few minutes back about, the encoding the information with the help of, a coin and with the help of dice, right? So coin is like representing 0 or 1. Dice is having about 6 states, whereas if you look at the qubit, you are having infinite number of states, right? So meaning what? Your storage capacity is being increased exponentially. Now, when you double the more number of qubits that you add, the amount of, the amount of storage also would get added. Now, and on top of that, bringing superposition gives massive amount of parallelism, right? So Imagine there is a mathematical operation on 2 power n number of numbers, and if they are encoded in classical computers, we require about 2 power n number of steps, or else you need parallel processors, right? But the same operation we can solve on the 2 power n numbers, which can be encoded by just n number of qubits, and you can solve it in one single step, right? So this particular phenomenon makes solving the complex problems very much easy, right? Now we talked about superposition. Mathematically, I think, especially the researchers, who are writing the programs and all that, if you see here, we will come to, in the literature, how do we represent? We say 0 or 1 in the case of classical. In the case of quantum, we call this as a ket representation. So this is called ket 0, this is called ket 1, right? So a qubit can be either ket 0 or ket 1. We call that as the basis states, right? So basis states of a qubit is ket 0, ket 1. Now, we also said about a state called superposition, meaning what? A qubit can be in the superposition of both 0 and 1. But then the question is, how do you write such state? So typically in the literature, we say a qubit in the form of xi, and this is called ket xi. What people write is alpha ket 0 plus beta ket 1. This is called a single qubit being in the superposition of both basis state ket 0 and ket 1. So this is the superposition state, right? Now, what are these alpha beta? We said ket 0 is the basis state of 0 state, ket 1 is the basis state. Alpha beta are called probabilistic amplitudes. These are called probabilistic amplitudes, right? Few minutes back, we said we are moving from the deterministic class to the probabilistic class. Now, this is the qubit which is in the superposition state. This is called superposition. And also a few minutes back, we said opposite of the superposition is called measurement. So the measurement over this particular qubit will bring the qubit state either to the ket 0 state or ket 1 state. So measurement will bring this to either ket 0 or ket 1. Now, whether it is settled down to ket 0 or ket 1, we can only tell in the form of probability. So the probability of resulting into the ket stereo state is mod alpha square, and resulting into the basis state of ket 1 is mod beta square, right? So I cannot deterministically say that it will measure into the state of ket 0 or it will be measured into the state of ket 1. I can only say that the probability of getting an outcome of ket 0 is mod alpha square. Probability of getting the ket 1 is mod beta square. These probabilistic amplitudes are the ones that will get changed when you are iterating over the, when you are computing with the programs, right? So this is the superposition state, right? Now imagine we have about 3-qubit system. How do I represent such a 3-qubit system in a superposition state? You can very well see I have possible states of ket 0, 0, 0 to ket 1, 1, 1. And you can see this is called probabilistic amplitudes, right? Of course, this is the equal superposition that is for the example that is shown, but it need not be, right? So you can have any value which is there between 0 to 1 for this probabilistic amplitudes. So this is the superposition what I spoke about, which is the fundamental phenomenon for the quantum computers. Next, we have another interesting phenomenon. We said about moving ahead from, I think the pointer is, moving ahead from locality to non-locality, right? We have said that we have said that when we have 2 qubits which are entangled, even if they are at far off place, measuring one particular qubit would impact the other. Okay, so 2 qubits, the example that is what is shown here is about 2 qubits that are, entangled. You can very well see that, they operate, the other loose term that what we can say is they are correlated, right? These are all 2 correlated bits. Measurement of one will impact the other, right? Which is through state operators called Bell states. We call it as in the quantum computing, right? Then we have another important property called decoherence, wherein which coherence is the one, decoherence is the one wherein which loss of superposition because of simultaneous or spontaneous interaction with the system, right? So, which is another parameter that is bringing into the quantum that I think, we will skip it for now. The measurement I spoke about, wherein which, any quantum system which is in the superposition state upon measurement would result into a particular state, and that would be decided based upon the probabilistic amplitudes, right? One of the example that is given is here, you have a 2 qubit system. So ket 00, ket 01, ket 10, ket 11, and you can see the probabilistic amplitudes of these particular states, and the probability to get that particular bit, which is, say, take an example, rightmost bit as the 0. Rightmost bit as the 0 is here, as well as rightmost bit as the 0 is here. So what is the probability of getting rightmost bit as the 0 is the probabilistic mod square of probabilistic amplitude of this. Similarly, mod square of the probabilistic amplitude of this is the probability of getting rightmost bit as the 0. This is how we calculate the measurement outcomes. So what I spoke is only a few one qubit simple examples, but building a large quantum computers, are essentially required to perform any type of meaningful calculations, right? But bringing such type of qubits is extremely sensitive because of the different environments, right? Requires isolation from the environment. This is another beautiful analogy or example wherein which a classical scenario, how a traditional computer would work for a particular task of, say, take an example, you have a logistic company that needs to find, most efficient route, from a particular origin to a particular destination. You have 3 origins through 3 different destinations. A traditional computer requires to, explore all the types of, the routes that are there, Whereas when you look at the, quantum, you can very well see that due to the properties of quantum nature, one of the property we talked about, the entanglement, we are able to calculate all the probabilities at once and evaluate all the options simultaneously, right? So this is one of the beautiful analogy or scenario or a use case that you can very well see that the power of quantum, where it can be applied, especially in solving certain class of problems. Having shown that, you can identify that, what class of problems a quantum computer can be applied. At the same time, wherever the problems where such as a sequential set solutions would be fit enough, our traditional computers or classical, problems classical computers would solve. Now, what we have seen in the previous scenario is just with the 3. Now you extrapolate, imagine you have about 10 origins and 10 destinations. A classical would require about 100 unique options to be explored, whereas, quantum, at a massive entanglement and other features of quantum, people are able to explore all the options at once, right? Now, having seen the building block of quantum is the quantum bit, the superposition and entanglement. Of course, there are, as I said, other phenomena, but what next would come into the quantum scenario is the quantum gates, right? We all know the logical gates that what we have seen. So you need certain operators to operate on the quantum bits. So what are those operators? They are nothing but the quantum gates, which are the basic units of operators on the qubits. So fundamentally, they are operators. fundamentally they are operators, meaning if you look at in the literature, they are called unitary operators. Especially, I suggest these, the PG or PhD scholars to understand, why they are called unitary operators, right? If you know what is the fundamental unitary operator behind a particular gate, operating with the particular gate would be very, very easy. So any gate is nothing but any gate would be a building block of a fundamental unit for a circuit, right? So the number of qubits, the number of qubits in the input and output of a gate should be equal. That is one of the fundamental condition. Similarly, any gate which acts on n qubits is represented by 2 power into 2 power n unitary matrix. So what are the various gates we have that we will see? One of the fundamental gate is about the Hadamard gate. This particular beauty of this gate is that this gate, will take the qubit and transform it into the superposition state, right? So how do you represent that particular gate? Few seconds back, I said that any gate operation is a unitary operator and it is represented in the form of a unitary matrix. So this is the matrix representation of the Hadamard gate. So take an example. You take this any basis state of ket 0 or ket 1. When you apply the ket 0 on this particular unitary matrix, what is the outcome you get is 1 by root 2 ket 0 plus ket 1. Now it is very simple to calculate. So you take ket 0, apply the Hadamard matrix operation, and what you get is the superposition operation, superposition state. Similarly, you take ket 1, apply the Hadamard, what you get is the superposition. You can very well see here, there is a difference in the sign. When you take ket 0, the superposition, what you get is 1 by root 2 ket 0 plus ket 1. When your basis state is ket 1, when you apply the Hadamard operator, what is the resultant superposition state is 1 by root 2 ket 0 minus ket 1, right? So this is called phase difference. This is called phase difference. Based on this phase difference, you have certain techniques called phase estimation and phase kickback, right? Phase kickback, which are fundamental quantum techniques. These are called quantum techniques. Based on these quantum techniques, you have quantum algorithms. Your Grover algorithm or Shar algorithm are all based on fundamental quantum techniques. I have noted here two such type of techniques called phase estimation and phase kickback, right? Fundamentally, what is phase? You can notice here, when you have a basis state, when a Hadamard operator is applied, you can see the difference in the phases, right? So this phase need to be estimated. Of course, what we have shown here is for a single qubit, right? The system complexity gets increases when you have multiple qubits. When the multiple qubits are entangled, you will have much more complexity. So accordingly, you have a techniques for phase estimation, phase kickback, and based on those techniques, you are having the quantum algorithms. Similarly, you have different other gates. Some of the other gates are called Pauli X gate, Pauli Y gate. What is the job of that? These gates are, say, take an example. If you notice Pauli X gate, this is the matrix representation of the gate, which is an unitary operator. So take the basis state either in the ket 0 or ket 1, apply the unitary operator of X. What you can notice here is that when you give ket 0 as input, you are getting ket 1 as an output. When you get ket 1 as an input, you are getting ket 0 as an output, right? So it's called flip, right? It's called a flip operation, which is performing over the qubits. So, and hence it's called bit flip operator. It's a single qubit operator, which is called a Pauli X gate, and it is performing bit flip operation. So X over ket 0 gives you ket 1, X over ket 1 gives you ket 0. Similarly, you have other operators called Pauli Y gate, Pauli Z gate. Now you can notice very well that, as I said, Pauli X gate is doing the the bit flip, and there is no phase flip. Whereas Pauli Y gate in addition to flipping the bit, it also flip the phases. Now you can very well see here. Imagine you, of course, the slide do not have the Pauli Z gate operator, but Z over basis state ket 0 will give you ket 0, but Pauli Z gate over ket 1 gives you minus ket 1. Meaning what? You are having bit flip as well as the phase flip, right? Similarly, if you apply Pauli Z gate, you will have, you will have no flip of the bit, but you will have the phase flip. So this is bit flip, this is bit flip and phase flip, and this is only phase flip. So like this, you have multiple gates. Of course, there is another important gate called C0 gate, which is called controlled NOT gate, and it acts on the 2 qubits. And of course, you can see very well, since it is a 2 qubit system, you are having a control bit and you are having a target bit. So what happens when your control bit is 0, target will do nothing, whereas when the control is 1, target gets flipped, right? So you can see very well 0, 0, 0, 0, 1, 0, 1. But when control is 1, you can very well see that target is getting flipped, right? So when control is 1, what is happening to the target is getting flipped. So it's called C0 gate. And this is the matrix representation of the C0 gate, and this is the circuit representation. So like this, you have multiple gates. So one has to understand the different gates in the quantum and their corresponding the operators. So the matrix operators. Of course, on the right side, we have the classical gates, and on the left, you can see very well the multiple gates, right? You can see single qubit gates, you have 2 qubit gates, and you have 3 qubit gates. So these are the essentials for us to understand next circuits. So we know that we have the bits, qubits we have seen the Q gates. Next, what we have is obviously would be the circuit. So when you have multiple gates being connected to perform a particular task, what you would achieve is the circuits, right? So it's a model for any, of course, not only for quantum, but even for the classical, right? So for computation purpose, where you are going to connect the sequence of gates, and hence, they are all linked through, the wires, meaning, forming a particular circuit. Now you can say also that depth of the circuit is the number of the qubits that what you have, and as well as the width of the circuit is based on the number of qubits, and then the depth of the circuit is based on the number of the gates that what you are having in the circuit, right? You can see Hadamard gate, this swap gate, Toffoli gate, and you can see these are all the qubits, qubit 1, qubit 2, qubit 3, right? And then there are operators on the qubits, and those operations sending the output to the other qubit environment based on the type of the operator we have, and finally we are going to have the measurement. So you can see this is the measurement operator. So we have the circuits. Now based on the qubits and circuits, as I said, we are having quantum techniques. Especially, I spoke about phase kickback and phase estimation. There is another technique called quantum Fourier transform, which is an analog to the discrete Fourier transform. The idea of the quantum Fourier transform is going to take the qubits in a basis state and perform the system in the form of multiple quantum superpositions. This particular technique is the fundamental for the SHAR algorithm. So meaning, suppose somebody is saying that I'm interested in security and wanted to understand the SHAR algorithm, one has to understand quantum phase estimation and as well as quantum Fourier transform to understand the SHAR algorithm. Similarly, suppose somebody says that, no, I'm interested in performing the search operations or search related tasks or even optimization related tasks. Obviously, people would be working on the Grover algorithm, and for that purpose, one has to learn the technique of phase kickback and then phase quantum phase estimation. Now, the understanding those techniques itself would, different sessions. So my job today is to introduce or maybe tell about those techniques. So as I said, you have the qubits, you have the Q gates, you have the quantum circuits which are connecting the gates. Next, we run or we build algorithms on top of these, the circuits that what we have. These algorithms are essential. Of course, no algorithm, we can't do anything, right? So these algorithms, of course, two popular algorithms I spoke about is the Grover or Shor algorithms. These are all the fundamental for the quantum, right? People are now looking and searching for the new set of algorithms that can solve the various other problems. That's why whenever you see certain research calls, you will see that people will be asking to design the new set of algorithms. So the existing algorithms that are there are trying to solve two fundamental problems of factoring and searching. Searching, I already said. The other problem is called factoring. Now, we all know that, imagine I have two numbers called, Q and N. Suppose somebody asks you to find the product of these two numbers. Easily one can perform multiplication and then say that, some P is equal to Q into N. This is very easy, finding the product, right? But the same problem given in a different manner, meaning what? Somebody gives you P, asking you to find the Q and N, meaning that we are trying to find the factors, right? So finding the product of two numbers and getting the product value is very, very easy. Whereas giving a single number, finding the factors of that number becomes complex. Now this problem becomes much more complex when you are trying to find not just factors, but rather you are finding the prime factors, right? So that is becoming much more complex. Classical computers don't find it feasible to solve this particular problem, and hence we are having the security algorithms such as the RSA, Diffie-Hellman, which are asymmetric algorithms. We are able to depend on them because we are not able to solve this problem in a classical scenario. But with the quantum, especially with the Shor algorithm, we are able to solve the factoring problem, and hence your asymmetric cryptography is being this one. So now I'll just quickly give about the Grover algorithm, one of the fundamental algorithm in the quantum computing, and which is providing a quadratically speed up solution, especially to the unstructured search issues, right? We have seen 2-3 scenarios of unstructured search. One, we talked about the library. Another one, we talked about the finding a particular SIM card number in millions of SIM card numbers, right? So this algorithm will dramatically reduce the number of steps required with the help of quantum, right? So how it is doing it, or what is the beauty of this? Imagine that we have about unsorted data that has about n number of entries. Now we also said that so far, with n number of elements, the worst case scenario for a classical computer is you need to look for into that solving that search problem with n number of queries. The average case is n by 2, right? We said Grover would solve it in square root of n. But what is that? What that it is doing to solve that particular problem? So it uses the quantum features. Number one, superposition. So, okay, with the help of superposition, what it is doing? It is checking all possible scenarios, meaning all possible states or all possible solutions at once. It is checking all possible solutions at once. And then what it is doing? It is amplifying the probability of the correct answer, right? So if you notice, I have drawn, this is one step, meaning checking all possibilities at once. That is step one. And then amplifying the probability of the correct answer is the second step, meaning there are two important steps. Of course, there are multiple steps, but essentially, if you split the quantum Grover algorithm, we have achieving the superposition. Of course, I should say this is step one. And then checking all possibilities at once is step 2. And amplifying the probability of correct answer is step 3. So totally there are about 3 steps in the Grover algorithm. So achieving the superposition, checking the all possibilities, and then amplifying the probability of correct answer. So a few minutes back, we said checking the or getting the superposition, we have the one of the operator called Hadamard gate or Hadamard operation to achieve the superposition, right? Then checking all possibilities at once is called quantum oracle. That is the job of quantum oracle. It's called a function which is looking at all possibilities at once. Then you have the finding the or amplifying the probability of the correct answer. So amplification, right? So if you can split the Grover algorithm, one has to say superposition, quantum oracle, and then amplification, probability amplification. These are the three fundamental steps that would be there. So based on that, you can see the algorithm that goes. You have about a unsorted database of n number of items. So obviously, when you have n number of items, you can represent in the form of 2 power n, and then you have of able to achieve. You should be able to achieve order of root n, right? This is the quantum oracle, that I spoke about, where in which if you are looking for a particular item, and if that item is available, if that particular item is available, the oracle is going to act in this particular fashion, right? So, if the item is available and if the item is not available, and it is going to, you can notice here, if the item is available, we are saying minus of that basis state, meaning what? We are actually changing the phase, right? When I say changing the phase, you know very well that what is the gate operation that is required to change the phase, right? A few minutes back we said about, right? So this is about the quantum oracle. Now your algorithm starts. Your initial state preparation of the algorithm, meaning giving the input. So start with n number of qubits, then apply the Hadamard operation to create a uniform superposition. This is your Hadamard operation in the Grover algorithm, right? Then I said about amplitude amplification. You may get a doubt. When oracle is checking the possibility of getting an answer, what is the need for amplitude amplification or increasing the probability of getting the answer? The simple reason is that, when we go back to a few minutes, we said in a deterministic manner, we cannot say that what is the output of or outcome of the measurement. What we said is that we all can tell this is the probability of getting this answer. The job of Grover algorithm amplitude amplification is to increase the probability of correct answer. Now we know that at a particular point or a particular location or a particular index, your desired value is there. But since it is in the superposition, meaning you have the probabilistic amplitudes attached to these states, and hence when you measure it, outcome may be in one of the state, but I don't want any state. I want the correct state to be produced as an output. And for that purpose, what I should do is I should actually increase the probability in a way that actually, in a crude sense, that I'm doing a kind of a rigging so that the candidate I wanted to win, actually I'm making them to win. That's the fundamental philosophy of this amplitude amplification, right? So for that purpose, there are two more operators called phase inversion, which you would have noticed in the oracle, and then you have a diffusion operation, so that your probability of getting the correct answer get enhanced, right? So these are the example of Grover algorithm. Imagine you have about, just for our illustration purpose, we have just taken about a few set of, I think 10 elements are there. So the idea is that whether you have a 72 in the particular array or not, right? Since there are about 10 elements, you obviously worst case scenario of 10 checks, right? So the first step of Grover is that, you are keeping, the probabilistic amplitudes, equal amplitudes through your superposition operation. This is the first step. Now you apply the oracle. So oracle says that, yes, a particular location called this particular index, you have the element. Now, the question is that it's not that identification of the element is the job of Grover. It is that to say what is the index. Now, for that, you need to get that index value out. Initially, you are having the amplitude values equal. So when you measure it, the system may get either 0 to 9 in any manner, right? So now the idea of this Oracle amplitude amplification is to increase the probability of getting this particular index 6 as an output. Now, how do we do it? Right? One is the first step is to flip the phase of that particular index. And after that, we are doing through diffusion operation. The diffusion operation is by performing first step of diffusion operation is computing the average amplitude of all states. Once the average amplitude, obviously we know that we have about 10 states. Each amplitude you sum it and then divided by 10, you get the average. Then after that, we reflect each amplitude towards the average. That step, if you can see here, by performing the reflection, you may get a doubt what is reflection. That I will talk about in the next slide. But when we reflect it, you can very well see the amplitudes of different indices, right? Earlier, you have noticed the amplitude value is 1 by root 10, meaning about some value. Now the new amplitude values is 0.253, 0.253, and whereas your index value 6 is 0.885. Your index 6 is the one having the element 72. If we do not do this particular amplification, you do not know which index you will get when you measure it. But this amplitude amplification step is required so that when you measure it, you get the index value of 6, right? So now what is happening? Your probabilistic values, mod 0.253 square, mod 2.3 square. Now probability of getting 6 would be mod 0.885 square, meaning you are having a higher probability of getting index 6 value. So these are the formulas. I said about reflecting the average, so you know how to calculate the average. So reflection about the average, meaning you take the new average by performing 2 into the average value that we have and then old average value. So for all the indices 0, 1, 2 up to 5 and then 7, 8 and 9, the earlier amplitude value is 0.3 and the new amplitude value is 0.2528. Whereas for the target element of, the index 6, right? What happened is you get a better amplitude value. Meaning what? When you measure it, your probability of getting index 6 has got increased when compared with the other normal elements. That's the beauty of the Grover algorithm, right? After all, it has only 3 steps: putting all possible states in the superposition, number 1. Number 2, applying the Oracle function. Number 3 is about the amplification, right? So, and of course, not with one simple amplification, we should stop, but we need to iterate it multiple number of times so that on an number of times we need to iterate it at least about root over 10. So the 3 iterations need to be done so that we get higher probability we get index 6, right? So it is faster. The reason is what we have done. If you look at in the classical scenario, worst case scenario, we need to perform 10 checks to get the index value 6. Whereas in the case of Grover, you have done superposition, you have done this, the Oracle application, and then iterating over the, the amplitude amplification over root n number of times. So meaning, your Grover algorithm is able to find the solution is close to 3 number of iterations, which is about root n, right? That's the beauty of these algorithms. So of course, now what I spoke about is the Grover algorithm. We have other algorithms such as Shor algorithm, the Zosa algorithm, Vazirani algorithm, Simon's periodicity algorithm. Each is doing different tasks. So like, you have hardly about 4 or 5 such beautiful algorithms. any task that you can take it to these algorithms, you can solve it. But of course, these algorithms don't require for solving certain classical tasks, right? So now we all know, we have seen recently in everywhere that how the quantum computers would look like. I think this is one of the most popular quantum computers that we have seen about superconductor quantum computing environment created by IBM. So if you notice, or if you closely observe what would be there in that, I think, ideally, we have IBM's superconducting chips that would be there, wherein which tiny electrical circuits would be encoded as the qubits, and they would be manipulated with the help of microwave pulses. That's what is the superconducting IBM devices that what we are seeing in nowadays everywhere. On top of that, we have others such as trapped ion chips, wherein which atoms are used as the qubits, and they would be manipulated with the help of laser beams and then microwave antennas. Similarly, you have other quantum computing environments coming with the help of photonic chips, wherein which photons are used as the qubits, and these photons would be manipulated with the help of splitting and recombining with the help of light waves. So especially, those who are learning about the QKD, where, we have people are sending the information qubits in the form of photons, right? So people can look at that type of environment, right? So each type have their own properties and their own usage. Especially as I said about QKD, where you are having quantum communication, photonic devices are making mark, and each company has their own way of building the quantum computers. IBM, as we said, it is using the superconducting one. Similarly, the Google, and everyone are coming with their own supremacy statement saying that their computers are performing better, or they are able to achieve higher qubits and all that, right? So in a very detailed level about the superconducting environment, you can very well see here, fundamentally your quantum qubit chips would lie somewhere here at the end of this particular environment. The rest, everything is about making these qubit chips operate in a effective manner, and for that purpose, you are having about liquid helium maintained with a high low temperatures, so that there will be no much significant impact from the outside environment. Similarly, you have gold coated metals, so that extra heat coming from the outside environment would be minimized and then protected. And fundamentally, you can also very well see that this environment is connected to a traditional computer classical environment, so that that controls this overall environment. And finally, when you have this output coming from the qubit environment, that need to be fed to the classical systems and then analyze it further, right? So especially for the students and the scholars who are enthusiastic to play with around, there are platforms available from IBM, Amazon, and then in terms of there are free environment. Of course, emulators are there. People can play with these environments, but with very limited number of time that they are giving, and with a limited number of qubits also they are giving. But for that, there is a long way to go, so that people will be able to access the higher qubit environments for the research and academic purposes. But this is all about the fundamentals of the quantum. We have talked about the basic phenomenon of quantum features. We talked about the fundamental blocks of qubits, gates, then circuits. Then we have seen the algorithms. Of course, we have seen about one of the algorithm of Grover algorithm. Then also about there are certain myths about people are run because of that large hype that is being created. Number one is that people believe that there will not be much. One of the myths is that quantum computers would not be commercially available, but I think down the line of 4 to 5 years, we may have the commercially available quantum computers. Even if not physically, we are able to be there with them, but we can access them through the cloud environment. Then another myth about especially the student and scholars, when we are talking that qubit can be there with a 0 and 1, we say always that bj qubit will be there at 0 and 1 at the same time. But ideally what actually it means is that it is about linear combination of 0 and 1. It's not that simply 0 and 1, it is the linear combination of 0 and 1, wherein which you have the imaginary numbers in terms of your alpha and beta, right? We said a qubit is there with the 0 and 1. We didn't simply write that ket 0 and ket 1. We said alpha ket 0 and beta ket 1. So, this statement do not have this alpha beta values. We keep saying that, qubit can be there with the 0 and 1 at the same time. Actually, it is with a linear combination of, real or imaginary numbers, right? This alpha beta are the such numbers. Next, the quantum computers will replace classical computers. Like right now, I'm sitting in front of my desktop and giving me my talk. So no, it's not so, right? Now, as I said, we have certain specific set of use cases where quantum would perform very well. But there are n number of use cases or real world problems where classical computers, they remain vital for all our day-to-day tasks. Essentially, the environments where you require huge set space to be crunched in a very small amount of time, and perform an optimization, provide certain rapid communication. So such scenarios, quantum computers have a role to play, and especially the complex optimization problems. But otherwise, your classical would always remain vital, right? The quantum computers solving the classical problems. I think majority of the researchers, especially who are working with the quantum computing and machine learning, many people, they would come and say that, hey sir, I have applied this version of the machine learning in the quantum environment, but my accuracy levels are not good, or I have not received the good accuracy and all that. So, there are certain areas where, they are not solving classical problems, but of course, there are several reasons. One is the environment, or, the implementation environment. It's not true quantum environment. As I said, we are implementing in the noisy intermediate state quantum computers. That could be one of the reasons. So again, there is a lot of debate going on that, right? So another myth is that quantum computers will destroy the entire encryption, no more cryptography and all that. That is another interesting myth or talk that people make it. But as I said, you have two types of the cryptography algorithms in terms of symmetric and asymmetric. Majorly, the impact would be there on asymmetric, and your symmetric algorithms are still secure in the terms of, by increasing the key space. And on the other side, even quantum computing is providing a security for exchange of the symmetric key through QKD principles, right? So, it's not that it will destroy the entire encryption and all that. In addition, people are building quantum safe cryptography algorithms. There are about 4 different class of algorithms in terms of quantum safe cryptography, called lattice-based cryptography, code-based cryptography, multivariate cryptography, and hash-based cryptography. And these are all ongoing research happening. And then they are actually trying to provide protection against the quantum computers. So meaning, it's not that, complete security is going to be obsolete and all, nothing like that. Similarly, if you look at the expertise or the knowledge that is required, either if I'm a computer science student thinking that, I will think only about the programming or even algorithm, not caring about the underlying phenomena of math or physics or this thing, or not even reading about it. We may not be masters over those physics aspects of it or math aspects of it, but at least we should also learn about them and understand them. Otherwise, when we are doing research, this would be tough to get the inference out of what actually we are doing. And similarly, same case holds for the other domain experts. Like, say, take an example, if somebody is there in math or physics, thinking that quantum computing, since it's a computing, it's only for quantum computers. I think, we have seen that, so far in the lecture, underlying philosophy is coming from all the disciplines of whether it is math or whether it is physics or whether it is computer science or even for the engineering, everywhere programming, everywhere everybody is involved, right? So these are the points. So I just quickly give about our work that we have done so far in this exciting area. Sometime back, we have received the in 2016, we have received the DST Cognitive Science Research Initiative grant in 2016 on building the quantum-inspired models. That's where we have, started working on that. We have got a couple of interesting results, especially in the area of quantum-inspired models in connecting the cognitive models of human cognition and modeling the human consciousness in the decision making process. These are some of the works what we have done towards that, especially in the decision making, how to bring the contextuality, how to bring the human consciousness, whether there is any quantum inspired models for that. So these are the couple of works that we have done. And later on, when we have also ventured into the machine learning aspects of it, we have worked with the quantum SVM for a specific application. And then this is one interesting work on security for encryption. We have a encryption algorithm called homomorphic encryption. We have discussed, this is only a literature, this particular work is a literature analysis of analyzing the quantum fully homomorphic encryption schemes. And of course, there is a contribution in terms of hierarchical memory management for the quantum for fully homomorphic encryption schemes, right? And this is the interesting work which this year, in the month of Jan, we got about the quantum machine learning for the network traffic analysis. One of the area which we are combining security, machine learning, is the one what so far we have done. But looking at this particular work, if you can notice that we have experimented with the several machine learning algorithms, of course baseline machine learning algorithms, and we have taken it to the quantum environment with the help of different encoding principles. We have seen the pure quantum versions, and then we have also hybridized the quantum and classical versions, and we have got some interesting results about the performance of encrypted network traffic analysis. So those who are interested, these are all openly available online. You can this one. And also we are teaching this particular course from past 2 semesters. The syllabus was framed somewhere around 2022. You can very well see that the syllabus is framed in a very comprehensive manner, starting providing an quantum computing introduction, the philosophy of the quantum features. Then we are talking about the math behind the quantum computing, talking about the matrix algebra, then vector spaces, then the Hilbert space, then about the building blocks of the quantum computers, then quantum information representation, then various techniques for the quantum computing in terms of Fourier transform, kickback, phase estimation. Then we also discuss about the quantum algorithms. Then, of course, students would also take these programming models that are there in terms of either Qiskit environment, a CIRC environment, or a penny lane environment. They do it, these algorithms implementation, right? So the lecture has, has tried to give you a broader perspective of the quantum computing, the features of the quantum world, then about the building blocks, then about the gates that are there. When we say gates, they are nothing but the matrices operators, unitary operators, and then play with them with the help of circuits, design the circuits with the help of these gates. Then we write the algorithms. One of the algorithm we have seen is the Grover algorithm. But rest of the algorithms, understanding the algorithms would require understanding these techniques, right? So until and unless we talk about these techniques, we cannot in detail discuss the algorithms. But again, to talk this more of techniques, you can very well see this is about 45 hours to 50 hours lecture, the content. So it requires, significant time. But, with what we have, we could quickly provide. I think, I could provide. Next, if there's those who are especially the students, undergraduate or postgraduate students, there is we all know that there is an ample amount of opportunities. Now there is a significant interest, especially even in the business community. People are trying to explore both in terms of machine learning or even a security or even a communication. I think the Center of Excellence talked about the various facets of the quantum computing, which is aligned with the National Quantum Machine. I think, these are the steps that one should do, especially with those who are interested to venture into the career in the quantum computing, understanding the fundamentals, then, acquire the relevant skills, then, pursue a formal education, maybe a degree. Of course, there are certain institutes offering a formal degree programs. Those who are in a PG, those who wanted to pursue PhD, of course, it's an exciting area. Always there are ample amount of opportunities. So those who are interested to connect with us and our lab, please feel free to write to my email, as well as, you can connect with me in the LinkedIn. Thank you very much for the patience listening. If you have any questions, I would be happy to answer.
Yeah, dear participants, please utilize the interactive session. Okay, thank you very much, Ashwin Kumar Garu. Your
Thank you.
explanation, till now, this is the first time I am listening your lecture. It's a great lecture. Hope our students, our participants will utilize. And at the same time, we are providing this lecture in YouTube also.
Wonderful.
Whenever they are interested, they can go back and they can refine, they can enhance their skills.
Sure.
Dear participants, if you have any queries, please interact with us.
Dear participants, if you are having any queries, you can post them on the chat also.
I think somebody is asking YouTube channel. I think they can. Yeah, can we use quantum computing in CNN? So so the answer to this question is, it is this, you can, take any machine learning model and then take it to the quantum environment, right? And implement it and execute. The question is that, you need to take care from the basic input to the output. In terms of, say, take an example, any classical information that should be encoded. So for that, of course, there are certain encoding mechanisms so that, your input would be transformed into the quantum state. Once you have a quantum state, then you can have the quantum algorithms that can be implemented there. Now, the point is that you have asked about a specific case of CNN. Ideally, what typically people do is, we take a classical algorithm. There may be a task that requires a huge classical computing power to be solved. So take an example in the case of SVM. We also know that, the kernel estimation is a complex task. So what typically people do is take the classical SVM, solve the complex task in the quantum, get the solution, and then, solve your classical problem in your classical computer. This is what is called hybrid. Wherever the literature talked about building the pure quantum versions, so far, people have not got, good, or higher or to the satisfaction level of superior results when they take the classical algorithms to the quantum. So even I've talked about our paper where, try to understand the encrypted network traffic analysis. The task itself is a complex. Your channel is encrypted. How do you analyze the encrypted traffic? There are beautiful machine learning algorithms people apply, and even deep learning algorithms. Accuracy levels are reported at higher levels. But now when we took it to the quantum environment, we didn't get better accuracies. So pure quantum versions, we didn't get better accuracy. So we have done an hybridization. Even with the hybridization, we have noticed, with the different encoding techniques, there are cases where occasion or a specific step where we got a accuracy levels to the classical scenario, but not a kind of a superior. I think to the answer your question, yes, you can take it, but it depends upon the task what you have.
Thank you, sir. Thank you for sharing your experience and expertise in quantum science and technology and showing the pathway to the quantum computing career also. So, on behalf of the Center of Excellence on Quantum Science and Technology and Jawaharlal Nehru Technological University, Kakinada, I express our sincere gratitude to our distinguished speaker, Professor Ashwini Kumar Cherkuri Garu, for delivering such an insightful and enlightening lecture. Sir, your valuable perspectives and expertise have greatly enriched our understanding and inspired all of us, sir. And thank you, sir. Once again, we are expecting similar sort of lectures from you, and we'll be connecting in future also, sir.
Sure, Amma.
Thank you, sir.
Thank you. Thank you.
And thank you all the participants
Thank you, sir.
for your kind cooperation.
Prasad, sir.
And
Thank you.
next Saturday also, we are having a couple of expert lectures in the series also. We'll be connecting soon.
Sir,
Thank you very much.
నాకు ఆ లింక్ ఇస్తుండండి సార్. నేను I will share it with my scholars also. It's wonderful
Sure.
sessions that you are arranging, for the
Surely,
benefit of
Ashwin Kumar
students.
Garu.
Thank
This
you.
is with the initiative of our Honorable Vice Chancellor, visionary man, Professor C.S.R.K. Prasad. During April 2025, after he becoming the Vice Chancellor, he entered into the JNTU Kakinada. He
Sir.
initiated a lot of activities related to enhancing the academics and research.
Wonderful.
Those are only 2 goals. Okay,
Yes.
we have conducted 2 days awareness session where MNIT Jaipur and a lot of experts came and addressed the participants. We will continue, sir. Surely I will share this link. Okay.
Thank you. We have scholars
Thank
so
you.
that we will share it with them also. Thank you, sir.
Thank you. Thank you very much. Please. I will keep in touch with you.